All right, so third time is the charm for some people with logarithms. I'm just going to kind of go over the basics for both inverses and log functions. So first, when we talk about inverses, we have to define what a one-to-one function is. A one-to-one function has to pass both the vertical and horizontal line test, which directly implies that the function has an inverse. So this function that I've drawn right here, no matter where you place a vertical line, no matter where you place the horizontal line, it is going to pass both of those tests. That means that this is indeed a one-to-one function. I could find the inverse of this function if I so desired. The technical definition is that each output of a function is associated with exactly one input. I don't love those definitions. I like the visuals personally, but it's kind of your preference. You can see this example of a parabola that I've put on the right here. It does pass the vertical line test, so that means that it is a function, but it does not pass the horizontal line test, because that theoretical horizontal line crosses 2 points. So we know that that parabola, that function, does not have an inverse function, because it's not one-to-one. Now, a common question can be to find an inverse. First of all, the inverse notation has this f, kind of looks like it's raised to the -1, so just be careful of that. It's not an exponent, it's just notation. Now, if you want to find an inverse, there's 2 steps. Swap x and y, solve for y. It's pretty simple. Verifying inverses is different. That's when you compose the function both ways, and if you're left with just an x in both case, of fogging and goffing, if you will, if you heard that from your pre-calc teachers. If those simplify to just x, then you verified them as inverses. So inverses lead us directly to logs, because we have a case here where we have y is equal to a to the x. You have your basic exponential function. If somebody asked you to find the inverse of this thing, there's not an easy way to do it. So we define a logarithm as the inverse of an exponential. So log with base a of x is the inverse of the exponential a raised to the x. Now let's just make sure we have an understanding of how to read logs, because I think seeing the log notation trips kids up sometimes, so I just want to go through that a little bit, if that's okay. Well, it's my video, so it's certainly okay. Let's say we have 9 is equal to 3 to the x, and we want to rewrite that in log form. We're going to solve for x. Obviously, you know that it's 2, but if I rewrite it in log form, we can kind of talk about what the log means when you read it. So in log form, it says x is equal to log base 3 of 9. So when you see the word log, what it really means is, okay, if I have a base 3, how do I get 9? You use an exponent of 2. So a log is always asking the question, what is the exponent? What should the exponent be? And certainly you could use the calculator to figure that out, but hopefully the nice ones you can do in your head. There's a couple of special logs. Log with base e, we shorten to natural log, ln. So I'm just highlighting the parts that are subbed out, because I see kids writing the e in certain places, or they keep, the ln all over the place. I don't know, it's a lot of crap you guys do. So log base e is interchanged with the ln, and the x stays there, or whatever it is that you're taking the log of. That is your natural log case. The other special case is log base 10, because it's so common that we don't even need to write the 10. That's kind of implied. It's kind of like an index for a square root function. You don't need to write it. So again, the log 10 is getting replaced with just log. And it is so common that we call it the common log. You've probably seen applications of both of these in physics, certainly bio. Here's a quick review of the properties of logs. I'm not going to spend time with these, but I just want to emphasize that you should know these rules left to right and right to left. You should be able to work with both of them, especially the last property there, moving that exponent. That's going to be very useful in calculus. Change of base formula is an interesting one. So I've seen it presented in a numerous ways. So let me just go through kind of like everything with change of base. So you are allowed to rewrite a log with any base you want if you re-express it as a fraction in this form, where b is literally any base. So since b is any base, you could just use ln. If you start with log base a of x, you could just say it's ln of x over ln of a. I think that's a pretty common way to use change of base that I've seen some pre-calc teachers use. So that might ring a bell, that might be familiar to you. The other thing you should note, let's just use some numbers here for this. Let's say I have log base 4 of 64. That means that I can re-express this log base 4 of 64 literally any way that I want. I could choose base 3, even though that doesn't really serve a purpose here. It is equivalent to log base 364 over log base 3 of 4. And I could re-express it using log base 10, which means I've got the common log. I don't even need to write it. I could use the natural log. These are all equivalent to each other. They're all proportional. So it doesn't really matter which base you use, but obviously there's advantages to using certain bases. Another fun fact, if you didn't know, regardless of what type of calculator you have, I think most newer calculators now can do log base 4 of 64 or log with any base. If you just type in log and then the number you're evaluating at, comma the base, that should spit out the correct answer, which in this case is 3. So let's actually solve an exponential equation using some logarithms. We have some sort of a equation here. It looks like this might have been an interest problem where we started with $1,000 and we wanted to know, when am I going to have $2,500? Totally reasonable question. Kind of strange that we're not just depositing some money into the bank though. But let's just go with it. What I've just highlighted in green is the exponential. It's the base raised to the exponent. That is what we need to isolate in this case. So I have to get rid of that 1,000. The 1,000 is getting multiplied out front, so I'm going to take a first step of dividing both sides by 1,000. That allows me to isolate the exponential. From here, you have a couple of options. So option one that I see a lot in pre-calculus, taking the natural log of both sides. The reason that you can do this is because it allows you to use that property from the beginning, where you can just drag that exponent, that t in this case, to the front, and that gets rid of the exponential. So let me just rewrite this line with the t out front. We end up with t times the natural log of 1.0525 is equal to the natural log of 2.5. And now it's really easy to get t by itself. I just need to divide by the natural log of 1.0525. And on a calculator, I can find that t approximately works out to be 17.9. Now, there is a different method that I actually prefer, and I don't have a lot of room here, so this is going to be a little crammed. Hopefully you can follow my logic. I like to take the log with the base of whatever my base actually is. So instead of doing the natural log, I'm going to take log base 1.0525 of both sides of my original equation, which, like I said, I don't have much room, so I'm just going to squeeze this into like 2 lines. And I really like this method because I think this kind of shortens the process a little bit. It's not as algebraic, but I think it's really nice because your base matches the base on the exponential, which means that all that just cancels out. And all you're left with is t is equal to log base 1.0525 of 2.5, which, if you think about change of base, you can see how that relates to the second to last line of the previous step, right? But regardless, I can get that t is approximately 17.9. So I prefer the method on the right, but it's really up to you guys how you want to solve your exponential equations using logs. Hopefully this was a useful overview of inverses and logarithms. I know the logs are tricky, so they do take a little bit of practice. Make sure you reach out to your teachers if you have questions on any of the log review.